All right, so here's our first video for Algebra 1. I've got a couple of things that I saw from people that did submit stuff to me, plus the stuff we've talked about over the last 2 weeks in our conferences, some things I want to go over. So if you're interested in hearing about reciprocals, a simpler way to do lots of crazy division and multiplication, and we're going to do a couple of exercises as well, showing you some of the solutions to some of these that you guys are confused about. If you're interested in any of that stuff, or like what negative versus minus, stay tuned. Let's start talking about some definitions. So first thing, people are wondering, what does this sign mean? And this sign is just an equal sign with a line drawn through it. So you can see something like this, like 2 does not equal 3. So that's all that means. It's just not equal to. Anytime you see a slash through something, odds are it means not. And then whatever else is underneath that is what it's referring to not being. Let's talk about negative versus minus. There was this problem that was giving some people some trouble. And there's a couple things that made this tricky, right? If I cover up this, obviously 11 times 6 ain't too bad. 66. 6 times 10, 60. 6 times 1, 6. Put them together. It's this that's the problem. Now this is an exponent, right? Because it's written up here and it's kind of small. So it's 6 to the power of something. So before we multiply 11 times 6 and get 66, remember, this is not asking us to do 66 to the power of something. It's asking us to do 6 to the power of something. So, for instance, if I cover this up, this would be 6 squared. So another way to read this would be 11 times 6 times 6, not 66 times 66, right? That would be completely different. So that's a key distinction. But if I pull this back, really what we're doing is, since we're using parentheses, we're saying this is some number, and that's the power we're going to take 6 to. So what does this represent? Well, this is 2 squared, which means 2 times 2, because square means times it by itself. So 2 times 2 is 4. And then 4 minus 3 is 1. So in here is basically just 4 minus 3. I'm going to take whatever that is as the power for 6. So of course that's 1. So 6 to the first is just 6. So we're going to get 66 for our answer. Now a lot of people are also asking about, is this a minus sign in here or is this a negative? So if I had something like this, right, is what we're really looking at right now. Is that a minus or is it a negative? Minuses are negatives, basically. They're the same thing. You can think of them either way. So when this says 2 squared negative 3, you can think of it like 2 squared plus negative 3, like that. And then I guess that would be how some of you would think of it as a negative, right, when it's with the number like this. Or it can be 2 squared minus 3. Either way, it'll be the same answer. This is 4 minus 3, which is 1. 4 plus negative 3, still 1, right? Adding a negative 3 is the same thing as minusing a positive 3. Exact same idea. And the reason for that is because when we minus a 3, what we're doing is we're heading in the left direction, right? That's what minus does. So here's my 4. That's what this is, right? And if I subtract 3, that's going 3 in the 1, 2, 3 left direction. So that's minus 3, and I end up at 1. Same thing with adding a negative 3, right? If I had 4 here, and I add, well, adding says go to the right, but then it says we're adding in the opposite direction, right? So when we add in the opposite direction, we're going to head to the left. And so that's going to mean we're not going to add this way, 1, 2, 3, but we're going to add in the opposite direction, 1, 2, 3. So that's going to get us 1 either way. So minusing 3 or adding a negative 3 are the exact same thing. Exact same thing. While we're on that topic, if I had 2 squared minus a negative 3, all that means is we're going to subtract. Subtraction goes to the left, but we're subtracting a negative, meaning that we're going to head in the opposite direction. So we're subtracting a negative 3, which means we're going to go to the right. Because, of course, subtracting a positive 3, like we just said down here, goes to the left. So subtracting a negative 3 needs to go subtract in the opposite direction. It's going to go to the right. So this right here, if I was starting at 4, I would subtract the negative 3. Subtracting 3 normally sends me this way, so subtracting a negative 3, 1, 2, 3 goes this way, which you might notice is the same thing as adding 3, right? That's why you hear your teacher say oftentimes a negative and a negative makes a positive. Now, I worry about that statement because later on, especially in Algebra 2, you're going to learn that a negative and a negative doesn't always make a positive. I also know in Algebra 1 and pre-algebra, I get some people say this, 2 negatives make a positive, right? And so when they see something like this, negative 3 plus -7, they think, oh, it's going to come out positive, right? 2 negatives make a positive. But that's not true. The difference is this is addition. So when we add all our negatives up, we're going to have a total of 10 negatives, right? A total of 10 negatives. Whereas here, when we have a negative and a negative like that, that's saying we're negating -3. To negate something means to change its sign. So negating -3 is just 3. Or you might see something like this, -2 times -5. That's when a negative and a negative makes a positive, because we're negating 2 and we're negating 5. A double negation is going to end up here. So when we multiply, 2 negatives almost always make a positive until we get to Algebra 2. That's true. But when we add negatives, not always, right? Sometimes it comes out negative, and sometimes it doesn't. So that's important to keep track of, that adding and minusing negatives, you really got to think what's going on here, right? We're putting things together. Whereas with multiplying or dividing negatives, you can kind of think 2 negatives makes a positive. But again, I would encourage you to think, if I negate a negative, I'm just doing the opposite, right? I'm going to have that -3 become a +3. What else do we want to talk about? We need to talk about multiplication and division. Let's start with this. So this is problem 121E. I'll show you what that looks like in your book. Looks like this. So 121E is this guy right here. Let's see if I can get it to show up. I can't get the mouse to show up, but you see it right there, right? Problem E. It's got that weird slash sign, and that slash sign just means division. What I would encourage you to do whenever you see a slash sign like that, especially in the first chapter where they're trying to like kind of trick you, change that into a division bar. So what I mean is, we're going to do this. So instead of 8 squared divided by 4 squared, with a slash, we're going to do 8 squared over 4 squared. And then we're going to add 3 times 4. And hopefully it should be clear by now that this is all one term, it's 12. And then this is all one term. And once we have like terms, 12 ones and however many ones this is, then we can add them together. I see a lot of people doing it this way. 64 is 8 squared, because 8 times 8. And 4 times itself is 16, 4 times 4. And then they figure out that this, when you divide 64 by 16, is 4. And that's fine, but I would encourage you to also notice this. 8 squared means 8 times 8. And 4 squared means 4 times 4. And since this is all one term, right, there's no addition or subtraction, we can divide or multiply in any order we want. So what I would do in this situation is this says I need to divide by 4 and then divide by 4 again. Or instead of dividing by 4 twice, I can divide by 16. That's what we did down here, right? So if I divide by 4 twice, that's the same as dividing by 16. So I'll divide by 4 twice. I'll divide this part by 4. When I do that, I get 2. And I can divide this part by 4 again. I'll also get 2. And these numbers change to 2's because 8 over 4 is 2, right? 8 divided by 4 is 2. So it's still timesing. So this is just 4, just like we said it would be down here. I think this is a little bit easier to figure out, because if you imagine you had a problem like this, maybe let's do 20 squared divided by, let's say, 4 squared. It's not a super hard problem, but it might take a little bit of doing. We can divide both 20s by both 4s, and what we get is 5 times 5, also known as 25. And if you've done the math out the other way, 20 times 20 is 4 with the 2 zeros, 400. And this is 16. It turns out 400 divided by 16 is 25, right? But I think it's much easier to think this. And it's also much more useful once we get to variables to be able to think like this and see what divides out. And again, don't say canceled out, because canceling can mean it becomes 0. And clearly in this case, it doesn't. It becomes 5. 20 divided by 4 is 5. 5 times 5 meaning 25. Let's take a look now at some more division and multiplication. Basically, there's a problem like this. A divided by B times C over D. And this problem that you guys have seen for the exercises has numbers in it. I think there's like 97 and 12 and 48 and numbers like that. I'm just showing you with variables, meaning that it's easier to show the concept of what's going on. It's not because those numbers were special necessarily. It's this. And let me show you what I mean. So as you can see, we have a lot of multiplication and division, and it's all one term. No addition, no subtraction. So we can do it in any order we want. So instead of just writing the top as A, C, B, D, divided by BDAC, we can notice that this says divide by A. And it doesn't matter when we divide by A. As long as we divide by A, we've done what the problem asks us to do. So instead of dividing D by A, and I don't know what that is, I'm going to divide A by A. See how there's an A up top? So A divided by A is going to be 1 because if that was 12 divided by 12 or 7 divided by 7 or 8 divided by 8, anything divided by itself is 1. So these divide out. And again, not cancel out, but divide out and become 1. Now, this particular problem I've set up to kind of demonstrate this a lot. So not all problems have this next thing happen, but we should be on the lookout for things we can simplify, right? A divided by A is 1. Let's get that out of the way. I also notice I have to divide by B at some point. So let's divide B by B. And again, I can do this because it's all part of the same term. If I had a plus B over here, I wouldn't be able to divide this B out, right? That's in a separate term. It's a separate idea. We're not dividing this term by B. We're dividing this term by B. So these B's divide out and become 1 because anything divided by itself is 1. The same logic applies for divide by C. I can divide C by C. So that's really nice. So I'll get 1s. For my last one, notice that D divided by D is also 1, so I get 1s in the top, 1s in the bottom. They're all multiplying. I'm just going to get 1 for an answer. But imagine I had a 2 in front of this D. Uh-oh, I think my camera cut out. Hold on one second. Let me reboot it. There we go. Hopefully it stays on. Okay, cool. So what if I had a 2 in front of this D? Let's focus. There it is. The D's would divide out. D divided by D is 1. And remember, this was originally 2 times D. So this 2 and a 1 are multiplying. So that really multiplies to 2. 2 times 1 is 2. And I want to make it clear, that's not an exponent up there. I just drew my 1 tiny. So D divided by D is 1. 2 times D, well, if D is now 1, 2 times 1 is just 2. So if I multiply across, 1 times 1 times 2 times 1, and that's how you multiply fractions, across. Not cross, across. 1 times 1 times 2 times 1 is 2. 1 times 1 times 1 times 1 is 1, so we get the fraction 2 over 1. So it turns out all these variables, even when I didn't know what the numbers were, simplify down to, this entire problem just simplifies down to 2 over 1, which of course is 2. So this is showing no matter what numbers I have, as long as all this stuff divides out and I'm left with just a 2, my answer will be 2. I could have had all kinds of crazy numbers in place of these letters, and as long as I had a way to divide them out, like I had a 73 here and a 73 there, and maybe a 5 here and a 5 there, and a negative 12 here and a negative 12 there, right? All those would divide out, and I'd be left with just this 2. Or if the 2 wasn't there, I would have been left with just 1. So like terms can divide out. And again, it's all part of the same term. If I had D's, B's, and C's over here with like a minus sign or a plus sign after them, right, that D would not divide this D. 2 separate ideas. Cool. All right, what else are we going to talk about? Every time I talk about something, the thing turns off. I'm going to turn it back on. I also want to talk about this. This is a real quick. Somebody was asking about this. There was a problem 1.13 was demonstrating that if you had 2 equal fractions, then you could infer something from that. So for instance, 6 over 12 equals 8 over 6, or 16 is an example. And these are true. They're both equal to each other because it is half of 12 and half of 16. And they were showing in the book how you can take this and turn it into 6 times 16 equals 8 times 12, and that would be a true statement. And it is true. If this is true, then this is true. And you might notice there's some like kind of cross multiplication going on here. And I try to avoid cross multiplication because it sounds so much like how we multiply normally with fractions, across. That is what's going on here. It's a little trick you can do to multiply this side by this denominator and this denominator by this side, right? And it ends up being true. Now, I wouldn't memorize that separately for lots of reasons. One reason being that you might screw it up with how you're supposed to normally multiply fractions. And very rarely do we actually get to do cross multiplication because there has to be an equal sign between them, right? Whereas normally we're just kind of multiplying, right? So one, that can be confusing and trip you up. And two, it kind of obscures and makes this thing seem really weird that we're able to do this thing. But if you understand what's going on, it's really obvious that if this is true, then this should be true as well. So we've learned that if we want to keep equations true, we can do lots of things, right? We can add a number to both sides. We can subtract a number to both sides. We can multiply or divide every single term on both sides, right? And that'll keep the equation true as long as we're not dividing by 0, of course. Well, we have one term on this side and one term on that side. So if I were to multiply, I wouldn't multiply top and bottom. I just multiply one or the other. Typically the top, right? We multiply by the top, divide by the bottom. So if I were to multiply this side, let's say by 12, right? I would have to also multiply this side, this term by 12. And what's neat about multiplying by 12, I didn't just make that number up, is that I'll times by the top or divide by the bottom first. And I could times by the top and get 72, and then 72 divided by 12 is 6. But probably what you should be seeing is that if I divide by the bottom first, 12 divided by 12 is just 1. Right? They divide out like we were talking about just a second ago. So altogether, I just get 1 times 6 over 1, which is just 6. Now over here, nothing divides out, right? So I'm just going to wait on that for a second so I can show you why I multiplied both sides by 12. I'm also going to multiply both sides by 16. Again, multiplying by the denominators. And the idea of multiplying by denominators is it gets rid of fractions, right? Because that's divide by 16, and of course times by 16 gets rid of it. And the reason it does is because 16 divided by 16, right? These divide out. 16 times 8, or 16 divided by 16, whichever one you want to do first. I'm going to divide first. Becomes 1. So we end up with 8 divided by 1, that's just 8, times 12 times 1. So we really just come up with 8 times 12. And here, when these divide out, we just are left with 16 times 6. So all I did was just get rid of division. And I took a true statement, did something totally legal. So of course I'm still going to end up with a true statement. So this works for any pair of true fractions. So I'll show one more example. 3/4 is the exact same thing as 6/8. And that's because I can think of 6/8 like this. Let me show you this on the side. 6 is just 2 times 3, and 8 is 2 times 4. And of course, these two things can divide out, right? So if they divide out, they become 1s. And look, 6/8 is the same thing as 2 times 3 over 2 times 4. And the 2's divide out. So it looks like 1 times 3 and 1 times 4. 6/8 is the same thing as 3/4. So they are the same. So I'm starting with a true statement. If I were to multiply the bottoms, or by the denominators of both sides, timesing by 4, and of course timesing by 8, some of these would divide out, like the 4's would divide out, become 1s, and the 8's over here would divide out, become 1s, and what I'm left with is 8 times 1 times 3 divided by 1. So in other words, 8 times 3 should be the same thing as 6 divided by 1, that's 6, times 4, times 1, otherwise known as just 6 times 4, and these should both be equal, and they are. This is 24, and so is this. So I don't like teaching a whole new trick for something like this, right? It's just get rid of division. We know how to do that, multiply, right? And so you can get from here to here, or from here to here, just by getting rid of that division, by multiplying by the denominators. We don't need to learn something called cross multiplication to do this, that you're going to get confused and use up here when you're not supposed to, when you're really supposed to be multiplying across. So instead, let's just get in the habit of when we want to get rid of division, we multiply. And that's how we can get rid of it. Speaking of that, I do want to take a look at some of these problems from the same section, 141 through 145. So let's jump to the book real quick and find that. So here's chapter 1.3. And if we go to the end of that, we'll find the exercises for 1.3. So it takes a while to get there, but there they are. And then of course, right after we get to the exercises for 1.3, the next thing is section 1.4. So now we're in 1.4 with distribution and factoring, which is something we're going to go over next week, but I also want to go over here because I know a lot of people had questions. And at the end of it, of course, we'll find the exercises. So the first thing we want to do is take a look at this, where it says, we've got 1.4. It says evaluate each two ways. Like the top line right here, it says we're going to multiply in the parentheses first, right? Let me zoom in on that. See if I can zoom in. So that, oh, uh-oh, I lost it. Let me zoom out a little bit. We're in section, where are we right now? 1.5, so I'm too far forward. Let me go back. Here we are. So right here in the top, it says we've got two examples. So example 1, you can see right, there we go, I'm mirrored right here. The top one does the parentheses first. 8 minus 3 is 5, right? And they get 10 when they multiply 2 times 5. Here, they distribute the 2. So instead of thinking I have 5 2's and that's 10, they said I have 8 2's minus 3 2's. So of course, if I have 8 of something and I take away 3 of it, I'm left with 5. In this case, I have 8 2's minus 3 2's, and so that's going to get me 5 2's, which is also 10. Or 16 minus 6, right? 8 2's is 16, 3 2's is 6, 16 minus 6 is 10. So we have options. They want us to do it both ways. So real quick, part A, I can do as 6 times 8 first. Let me switch screens. I believe it's this. Is it 3 and 5 for this one? Yeah, it is. So I can do this problem as 6 times 8, which is 48. Or I can do it as 6 times 3 plus 5, which is going to be 6 times 3 plus 6 times 5. Again, the idea that I have 8 6's, or I can think of it in pieces. 3 6's and 5 6's. Of course, added together to make a total of 8 6's. 18 plus 30, 48, which is the exact same answer we got doing it this way. And again, the reason I'm showing you multiple ways to do it is, one, we're going to switch to variables a bit eventually, and you're going to need to know that you can do this, that you can distribute the 6 to the 3 and the 5, right? We have 3 6's and 5 6's. But you also need to know this because sometimes 6 times 8 might be hard, or some problem that I give you, right? And if you break it down into pieces, it might be easier. So let's look at part B. Part B, the original problem, is the quantity of 4 plus 8 times negative 2. And so if I do this, there's two ways of thinking of it. I have 12 negative 2's. Well, 12 2's is 24. So 12 negative 2's will be negative 24. And then the other way to do it is to think, I can multiply the pieces by negative 2. So 4 times negative 2, and then we're going to add 8 times negative 2. And individually, what those will be is negative 8 plus negative 16. Well, if I'm adding negative 16, I'm going to total them up. I have 8 negatives and 16 negatives, total of 24 negatives. Just like we got up here. Because again, 4 negative 2's plus 8 negative 2's should be the same thing as 12 negative 2's. Part C, we've got 7 times 5 minus 2, which means we can think of this as 7 times 3, which is 21. Or we can think of it as 7 5's minus, because there's a minus sign here, 7 2's. Another way you might think of it, instead of 7 5's minus 7 2's, because there's a minus sign, is you might think of it as 7 5's plus 7 negative 2's, right? 7 5's, 7 negative 2's, and we're going to add those together. Either way works, because 5 7's minus 2 7's should be 3 7's, right? Same thing we got here. Or 5 7's plus negative 2 7's would also be 3 7's. So either way, we'll get the same answer. It looks like 35 minus 14, which of course is 21. Here it would be 35 plus negative 14, and of course adding a negative is the same thing as minusing, so 21. Part D, the last part of this problem, is 8 minus 13, quantity of 8 minus 13, times negative 3. And because we've got some negatives involved here, there's a couple ways to think about this. Either we can think about it part A, 8 minus 13 is negative 5. So I have negative 5 negative 3's, that's positive 15. Because 5 negative 3's is negative 15, so negative 5 negative 3's would be positive 15. Or we can think of it like this. 8 negative 3's, and then I'm going to put a minus sign down, minus 13 negative 3's. And that's going to be negative 24 minus negative 39. Minusing a negative is the same thing as adding. So it's really negative 24, positive 39. So it's going to come out positive because there's more positives than negatives. How many more? 15 more positives. And that makes sense, right? Because if I have 8 negative 3's and I take away 13 negative 3's, I'm going to have negative 5 negative 3's. And of course, that's positive 15. Another way to look at it is 8 negative 3's, just like we did here. But instead of minusing, what I can do is I can add negative 13 negative 3's. So in this case, I'm going to get negative 24, just like I did before. And then I'm going to add whatever this is. Well, this is positive 39. Similar to what we got here, right? We're minusing a negative. Here we're adding a positive because those two negatives right here, negative 13 times negative 3 is going to come out to positive 39. And we'll get 15 as well. Cool. So this idea of distribution of instead of multiplying by 3, multiplying by 5 and then multiplying by negative 2 and putting them together, that's distribution. It's a super important concept in algebra. Let's do some more practice with that. Let's take a look at this next example right here. It says Richard expanded this product, quantity of negative 2 times the quantity of 5 minus 3. So it looks like by expanded the product, what they mean is he took that negative 2 and he times it by the pieces, 5 and negative 3. So it looks like negative 2 times 5, that checks out. And then he said plus negative 2 times regular 3. And so the question is, where did he go wrong? Well, it should have been negative 2 times negative 3, right? Because that's what it says in the original problem right here, right? There's a negative 2. Where's my finger? There we go. It's a negative 2, and then right next to the 5 is a negative 3. So that 3 should have been negative. Or he could have thought about it this way. So let me write this down real quick. So we got two options. You can think of negative 2 times the quantity of 5 minus 3. You can think of it like this. Negative 2 times 5 plus negative 2 times negative 3. Again, right? There's both our negatives, so we can't put a negative here. It's got to be a plus sign. Or you can think of it as negative 2 times 5 minus, we're getting the minus sign from the 2, times 2, or minus 2 times negative 3. So in this case, we'd get negative 10 minus 2 times negative 3. Well, that's negative 6, so we're minusing negative 6. That's going to be negative 10 plus 6. We get negative 4. Whereas here what we get, and I'll do this one in red, is negative 10 plus, that's going to be a positive 6. And of course, that's going to get us negative 4 as well. So a common mistake that you might make, and looks like Richard did too, is you got lost in the sauce with the negative signs, right? Make sure we're timesing negative 2 times negative 3 like it says in the original, the top line, right? And not forgetting our negative along the way. 1.43 is one I really wanted to talk about for a lot of you guys. It says factor out a 4 from each expression. So they give an example. They've got 36 plus 44 equals 4 times the quantity of 9 plus 11. So let's talk about that example real quick before we go on. 36 plus 44. So two terms here, right? And both terms have something in common. They have a factor in common. Factor meaning multiplication. 44 is 4 times 11. And 36 is 4 times 9. So if you look, they have a common factor. Factors meaning numbers that multiply to make them. And the common factor here is 4, meaning that we can rewrite this as 4 times 9, the quantity of 9, plus 11. So if I had just given you this and told you to distribute, you would say, oh, 4 times the pieces, right? 4 times 9 plus 4 times 11, right? And that's exactly what we're doing here. We're taking 4 times 9 plus 4 times 11, and we're working in reverse. Instead of distributing to get to here, what we're doing is we are factoring out or pulling out a 4. So notice that we have a 4 in this term, right? And a 4 in this term. So if we pull out that 4, what we're left with is 9 plus 11. Or 24s. And you can see how 24s, which is 80, is the same as 9 4s plus 11 4s. Because of course, if I have 9 of something and 11 of something, in total I have 20 of that, right? So 9 4s plus 11 4s is the same thing as 24s. So we can add it up either way. So what they're doing now is asking you to pull out a 4 from both terms, right? So we pulled out a 4 from both. What's left is 9 from the 36 and 11 from the 44. I don't even think they're asking you to solve this. Let me double check. No, it doesn't look like it. It looks like they're just asking you to factor it. So turning this problem into this is what we're trying to do here. Changing this, 2 different terms, into 4 times something. So technically all one term, right? 4 times something, whatever 9 plus 11 is. This is a super, super important technique, factoring out or pulling out. So the next example in 1.4.3, part A, it says 88 and 16. So we want to turn an addition problem into a multiplication problem. And what we're going to do is we're going to factor out a 4, because that's what they asked us to do. So if I factor out a 4 from 88, well, 88 is just 4 times 22. So what'll be left over is 22. And 16 is just 4 times 4. So if I take out a 4 from this term, I'm left with this 4 here. So it looks like 88 plus 16 is the same thing as 4 times 26, or 4 times 22 plus 4. Part B, when it says to factor out, again, we're not solving, we're just turning it into a multiplication problem, taking addition and turning it into something times something. It says 400 minus 32. Well, just like I did up here, let's think about what I can turn this into. 4 times 100 is 44, and then we have a minus sign. 4 times 8 is 32. So both have a 4 in them. I can take out a 4 from both terms, this term and that term, and I can turn it into 100 minus 8. So it turns out 4 times 100 minus 4 times 8 is the same thing as 4 times 100 minus 8, or 4 times 92. And that makes sense, because right here we have 100 fours minus 8 fours. That'll be 92 fours. And that'll equal the same thing as 400 minus 32. So here's our factorization, that's what we call this, of 400 minus 32. And here's our factorization of 88 plus 16. Part C's got negative 24 plus 16 plus 72. So now we have 3 terms. And the first one I can rewrite as 4 times negative 6. Next one I can write as 4 times 4. And 72 I can write as 4 times, well, I know 4 times 20 is 80. So 4 times 19 is 76. And 4 times 18, I'm just walking back by 4s. 80, 76, 72. Must be 4 times 18. So all 3 of these terms have a 4 in common. And what's left over would be 4 times negative 6, 4 times positive 4, and 4 times positive 18. So it looks like all of this is the same thing as 4 times, if I add all these together, 16. 4 times 16. So there's our factorization of negative 24 plus 16 plus 72, if we take out a 4. Now you might notice in this problem, in particular, these 3 terms also have a common factor of 2. So we can also take out a 2 of that. We'll talk about that in a second. Or maybe not in a second, but in a week or so. Lastly, at part D, 92 minus 160 plus 36. Once you figure out that 92 is the same thing as 4 times, well, 4 times 20 is 80. So 21, 84, 22, 88, 23, 92. Minus 4 times 40, that's what 160 is, because 4 times 4 is 16. So 4 times 40 is 160. And this is plus 4 times 9. Once you figure those out, then you'll know that we're left with 23 minus 40 plus 9. So there's our factorization for these 3 terms. 2 more, and these ones go by pretty quick. Hopefully you've been skipping around based on what you need to review and what you feel comfortable about, and you're taking notes on what you have learned. They say we've got this, 99 plus 88 minus 77. This is problem 1.4.4. And then plus 66 over 11. Now this is an example where with numbers, you could add from left to right and then divide by 11, right? 99 plus 88, then take away 77, then add 66, and then whatever that number is divided by 11. However, if you know how math works, you know that we can divide, since this is everything divided by 11, we can divide the pieces by 11. Just like earlier we could multiply by the pieces when we were doing distribution, we can divide all the pieces as well, because multiplication and division are like 2 sides of the same coin. So if we do 99 divided by 11, that becomes 9. 88 divided by 11 is 8. 77 divided by 11 is 7. And 66 divided by 11 is 6. So now that I've divided everything by 11, all I'm left with is 9 plus 8 minus 7 plus 6 all over 1, because I divided everything by 11. And dividing by 1 doesn't really change anything, so I can kind of ignore that. 9, I'm going to put these two together first. 8 minus 7 is 1. So 9 plus 1 is 10. Plus 6 is 16. And 16 divided by 1 is just 16. Much easier than getting a giant number and then having divided by 11, right? Divide out all the terms if you're able to, right? And it'll become a much simpler problem. Now, you couldn't just divide some of these. So for instance, if I had like 99 plus 8 over 11, I couldn't say, oh, that'll divide out, right? That's a 9 now, but I won't divide this because 11 doesn't go into 8. You have to divide every term. So for those of you that are interested, how you would handle a problem like that, if you really wanted to divide every term, and maybe you would, maybe you wouldn't. If you really want to divide both terms by 11, what you could do is divide the first one by 11, which is 9. 99 divided by 11 is 9. And then divide 8 by 11, which is 8 elevenths. So if you really wanted to, you could, right? But it wouldn't divide out nicely. So I probably wouldn't want to do this. I'd probably rather do 99 plus 8 and get 107. And just leave it over 11. Could do that. Totally fine. These are both the same. You'll notice that this basically turns it into a mixed number, right? 9 and 8 elevenths. Last problem is 1.4.5. And that has two parts to it. And it's demonstrating this idea of dividing, right? And multiplying in any order we want. So we have this problem right here. And of course you could multiply the top altogether and then divide it by the bottom. But hopefully you're noticing that because this is all one term, we only need to divide by 7 once and 4 once. Well, luckily, 7 divided by 7 is really easy. Same thing with 4 divided by 4. So what we end up with is 1 times 6 times 1 divided by 1 times 1. So it's 6. That was part A. For part B, they give you this. 3 times 8 divided by 27. So some of you might have saw here, oh yeah, the 7s and 4s divide out. Be careful to make sure you can actually do that, right? It's all multiplication and division, so we can. If there were plus signs here, wouldn't have worked that way. So for instance, 4 plus 6 times 7 divided by 7 plus 4 would not divide like that. Even if this was 7 times 4 in the bottom. We've got multiple terms in the top. We have to divide the 4 by 7 times 4. We have to divide the 6 by 7 times 4. And we have to divide the 7 by 7 times 4. So things wouldn't just cancel here and here, right? Don't be getting in the habit of thinking canceling. We're dividing by 7 times 4. So each term has to get divided, right? There's 3 terms in the top here, whereas this is all one term. So might want to make a note about that. This does not work like this. Down here, it's less obvious what divides out. Because if you look, there's no 3 or 8 in the bottom. However, I can think of 27 as 3 times 9. And so now it's clear that the 3's will divide out and become 1. So we get 1 times 8 and 1 times 9. So 8 ninths is a simplified version of this. So again, look for common factors to divide out. Look for, combining terms in interesting ways to make your math easier on you, right? We've talked about problems like 102 minus 95 plus 96. It's much easier to start from here and get 1 and then add it to 102 and get 103 than it is to take away 95 and then add back 96, right? Anyway, I think that's all we want to talk about. Is there one more thing? One more thing, reciprocals. Last thing and then we're done. So reciprocals. Basically the idea is this. If you have a number, like let's say 5, the number that multiplies by 5 to make 1 is called the reciprocal. So whatever this number is the reciprocal. And in this case, the number you multiply 5 by to get 1 is 1/5. 1/5. Now, what's interesting about this is that if we were to think in terms of division, 5 divided by what is 1? Well, of course, 5 divided by 5 is 1. And so what we've basically learned here is that dividing by 5 gets you 1, or timesing by 1/5. They get you the same thing. So basically we know that 5 times 1/5 is the same thing as 5 divided by 5. And we know that 1/5 is not the same thing as 5, but timesing by 1/5 must be the same as dividing by 5. And so we've learned the relationship between reciprocals, that this idea of a number being flipped, if you notice, 5 is just 5 over 1, and if we flip that, we get 1/5. That reciprocals, dividing by the reciprocal or timesing by the reciprocal, is the exact same thing. And this might be useful when you see a problem like 3 divided by, let's do 3/2. What this is really asking is how many times does 3/2 fit into 3? Well, some of you know this is 1.5, so it'll fit into it twice. So the answer should be 2. But while dividing by 3/2 is kind of weird, if we times by the reciprocal, 2/3, it should be the same answer. Because again, timesing by the reciprocal is the same as dividing by the number, or vice versa. So here we know to times by the top or divide by the bottom. Here I'll divide 3's out and get 1. 1 times 2 is 2. So that means this answer is also 2. So oftentimes it's hard to think about division of fractions in your head. So it can be easier to think instead to times by the reciprocal. And the reason this works is because it looks like, just by checking out some math, that timesing by a number is the same thing as dividing by its reciprocal, or vice versa. So 1/5 is not equal to 5, but it is the reciprocal of 5 over 1. So they are reciprocals of each other. So one more example. If I wanted to do, let's say, 7 divided by 4/5, I could instead think of that as 7 times 5/4. And while it wouldn't come out nicely like this did with 2, it is going to be easier to do in my head than trying to think about how many times 4/5 fits into 7. So if I times by the top and divide by the bottom, I get 35 over 4. So it looks like 4/5 goes into 7, 35 over 4 times. In other words, that's just a little bit less than 10, right? Or a little bit less than 9, because 36 divided by 4 is 9. So 35 divided by 4 is 8 point something, right? I think it's 8.75. Much easier to figure out this one than it is this. So this is a super useful skill. If you don't know about reciprocals, dividing by the reciprocal or timesing by the reciprocal can get you out of a jam if you're not sure how to divide by a fraction, right? So keep that in mind. That's the same reason why like 8 divided by 1/2 is the same thing as 8 times its reciprocal. 16. 1/2 fits into 8 16 times. Anyway, I know it's a lot of stuff, but it's 2 weeks worth of things, stuff we want to get taken care of. I know it's like an entire class worth of video here, but hopefully you were skipping around and seeing what you could learn from it, and you're able to come back to it when you need to. My advice is write down the video and like the timestamp of when the topic's up. So if you learn something new, you can go back and review it later if you need to. So if you were learning about reciprocals, go back to where we first started talking about reciprocals, write that timestamp in your notes, and I think that could be helpful. All right, see you later.